So let's real quickly just take a look at this radiation pattern plot that we've got here. And the thing I'd like to point out is that this radiation plot is what we would call highly directive, meaning that the radiation points very strongly for this radiation plot in the z direction. It does not point very strongly, let's say, in a 45-degree angle from the ZY plane or something like that. So we would call this a very directional antenna. And we have ways to quantify the directivity, or how directional antenna is. And directivity is a metric of an antenna that tells us how strongly it points in a certain direction as compared to how it points in all other directions. So the IEEE defines directivity of an antenna as the ratio of radiation intensity in a given direction from the antenna to the radiation intensity averaged over all directions. So we say that the directivity, D, of an antenna in any direction is D of theta comma phi. This is just saying how directive it is in a certain direction, and that's equal to the radiation intensity over in that direction divided by the average radiation intensity for that antenna. And the average radiation intensity here is equal to the total power radiated by the antenna divided by 4 pi. So I can write another formula for directivity using radiated power instead of average radiation intensity, and that would be the directivity of the antenna is equal to the radiation of intensity of that antenna in a particular direction. And instead of average radiation intensity, I just write total radiated power by the antenna divided by 4 pi. And since that 4 pi is in the denominator, I just get 4 pi times the radiation intensity divided by the total power radiated by the antenna. And 4 pi is a unit of steradians. U is in units of watts per steradian, and total radiated power is, of course, in watts. And so we see that directivity is a unitless number. Typically, though, we're not interested in the directivity in a general direction. We're interested in the directivity of the direction that the antenna is designed to point in. And so we're going to usually discuss directivity in terms of maximum directivity, which is given the symbol D sub max. In some texts, you'll see the symbol D sub 0, and that is just equal to U max, which is just the largest value of the radiation intensity divided by the average value of radiation intensity for the antenna. So using our previous substitution, that's just 4 pi max radiation intensity divided by total radiated power. That gives us the directivity. And I want to do an example now to help clarify directivity. And what I want to do is find the directivity and maximum directivity for an antenna, for two antennae that were given the radiation power densities for. So radiation power density, as you'll recall, is a function of all three spatial variables. And for this first antenna, the radiation power density is given as some magnitude, and the pattern is given by sine of theta. And that whole thing is divided by r squared. And then the radiation power density for the second hypothetical antenna is just r theta phi. And it's real similar, but we're going to say it's a0 of sine squared theta over r squared. So remember that the radiation intensity, we just take radiation power density and we multiply it by r squared. Just saying this, right? R squared times radiation power density. And so U1 is, if I just multiply this here, I'm going to get a0 sine of theta. And U2 is going to be a0 sine squared theta. So what I need to do next to calculate this, since I've got U, I need to know what the total radiated power is, and radiated power is just equal to the surface integral of the radiation power density. And so for P1, it's going to be equal to the integral from 0 to 2 pi, integral from 0 to pi, A0 sine of theta over r squared times the differential surface element, which you'll recall is r squared sine theta d theta d phi. And I'm not going to do the math here. You can to test your skills, but it's pi squared times A0 watts is the total radiated power from that antenna 1. And antenna 2, it's again going to be the surface integral, but for A0 sine squared theta over r squared, and I'll just write the result to save you all some time. It's 8 pi over 3 A0 watts. So now I can determine the directivity using these formulas here, and the directivity of antenna 1 as a function of theta and phi is going to be 4 pi times mu1, which was, u1, which was A0 sine theta. And then I need to divide that by the total radiated power for antenna 1, which was pi squared over A0. And we can see that there's some cancellations that's going to go on here, and it's going to give us the result of 1.27 sine of theta. And then D2 is going to be equal to 4 pi times U2, which is A0 sine squared theta. We need to divide that by the total radiated power of antenna 2, which is 8 pi over 3 A0. And we can see that the A0s are going to cancel, and the 4 pi is going to cancel with the 8 pi, and that ends up giving us 1.5 sine squared of theta. D max is just, well, when are these values at their maximum value? And since both of these include a sine term, the max value is when sine, remember sine goes from -1 to 1, so the maximum value of this function is going to be bound in that region, so it's 1. So D max for antenna 1 is going to be equal to 1.27. It's a unitless quantity, and that's going to be when the sine of theta is equal to 1, and that's at theta equals pi over 2, of course. And then D max for 2, it's going to be when sine squared theta equals 1, which again is going to be at theta equals pi over 2. So here we've got a formula for the directivity of the antenna in general. It's just saying that it is a function of just its theta, and it's 1.27 times whatever that is, and similar here. And then we see that the points, the maximum directivity is in the pi over 2 direction, and it is 1.27. So that example hopefully helps to clarify a little bit about directivity, and if not, let's take a look at this plot. And what I've done here is I've plotted the radiation intensity from the previous examples, and I've just set A0 equal to 1. And what you can see is that if we were to extrapolate these plots of radiation intensity for sine, which is this bigger one, and for sine squared, which is this tinier one, you can see that they both form these donut shapes, but the sine squared function is a little bit skinnier, and by that it's a little more directional. It's narrower in this elevation plane. So we can therefore view directivity as a figure of merit that describes how well the antenna directs energy in a certain direction. And visually here we can see that the sine squared function directs energy better than the sine function does, and our visual observations kind of jive with the evaluation that we did numerically on the previous slide. And notice that I've been talking about max directivity here, and antenna will direct energy in all directions. And for example, in this donut shape, no energy is emitted in the plus z direction. So we would say that the directivity for both sine squared theta and sine theta in the positive z direction is 0. So it has a directivity in that direction. It just happens to be 0. So that is directivity.